Alright, so if we have the general form of our differential equation, this is the same general form that we've been working with. And all I'm doing is I'm writing, this would be the highest order, this is the nth order derivative. Of course, you would have that first in your differential equation. And then the next term, you would have the n minus 1th derivative. So it would be a sub n minus 1 of x to the n minus 1 times the derivative, the n minus 1th derivative. And that would keep going on and on forever until eventually you get to the point where you just have a sub 1 times x dy dx plus a sub o times y equals some g of x. So this is just the general form of a linear differential equation of nth order. Nothing really magical going on there. Alright, so if we were to try a solution in the form y equals x to the m power, where m is what you're trying to find, those m's, remember? That was with our auxiliary equation. That this m right here is a solution of the auxiliary equation. Just like we had e to the mx, if we were to try y equals x to the m, then we would have a m times m minus 1 plus b m plus c equals 0. All right, because how do we take these derivatives? It's not too hard to figure out how to take those derivatives. And then if we plug them in, we would have something of this order, which could be written a m squared plus b minus a times m, right? Because we'd have two m terms. If you distribute this, you'd have two m terms, so you'd have some b minus a times m plus c equals 0. And that looks like a quadratic equation, and so we can treat it like a quadratic equation. Once we solve for m, we're going to get one of three things, right? Just like before. We're going to get two real distinct solutions. We're going to get one repeated solution, real solution, or we're going to get complex conjugate solutions. Okay, just like with the e to the alpha x, and we were doing that. That's what we were doing before. Now we're looking at it, instead of using e to the alpha x, what if I was to use y equals x to the m? All right. So, we have three cases. Case 1 is if we have distinct real roots. So if we have distinct real roots, we have two distinct real roots, right? That's the s, it's plural. So we have two, usually we only have two because we're dealing with second order differential equations. So that means that we will have a m sub 1 and an m sub 2 that are real roots. Meaning they're real answers, real numbers. The y sub 1 would equal x to the m sub 1 and y sub 2 would equal x to the m sub 2. Once you figure out those two solutions, the linear combination of those solutions, your y sub c, would be equal to c sub 1 x to the m sub 1 plus c sub 2 x to the m sub 2. All right. So, for example, let's say that I have x squared d squared y dx squared minus 2x dy dx minus 4y equals 0. So if this is our differential equation, now you can write x squared y double prime minus 2x y prime minus 4y equals 0. That means the same thing, so I just wrote it as an alternate form before. Then if we were to let y equal x to the m, what would dy dx be, or y prime? It would be m times x to the m minus 1. So what would be the second derivative? So I would take that derivative again, the derivative of the first derivative, and I would get m times m minus 1 times x to the m minus 2. Now, if I take my differential equation here and I plug in my second derivative, my first derivative, and y, what would it look like? Let's see. I would have x squared times, I plug in my second derivative, it would be times m times m minus 1 times x to the m minus 2. Right? I'm just taking the second derivative and plugging it in. Then I'd have minus 2x, and then the first derivative, times m times x to the m minus 1. Then I would have minus 4, and then where's your y? We said we want to let the solution equal m to the x. So y equals m to the x. So where I have a y, I'm plugging in, and I said m to the x. I meant x to the m, sorry. X to the m. All right. So if we plugged all of those in, we would have that. Now, if I was to take and factor out an x to the m, so let's just factor out an x to the m, and let's see what that would leave. You got to be careful. Now, how about this? How about before we factor out an x to the m? So let me go back a little bit. We're still going to use that. But before we factor out an x to the m, let's see if we can multiply any bases with different powers. What am I talking about? Can we multiply x squared times x to the m minus 2? Can we multiply x times x to the m minus 1? Well, we treat those just like we would any number to a power, or any constant to a power, or any variable to a power. If you're multiplying bases, it's the same base with powers, you add the powers. So what would that leave if I added, if I said 2 plus m minus 2, then I would have just x to the m, right? Because the positive 2 and the negative 2 would cancel out. Alright, let's do the same thing here. We have x to the first. We have x to the m minus 1. Add the powers, and that leaves just x to the m times m. And then there's nothing, there's no other x term with the last term, so we leave it just like that. Now, we can factor out an x to the m very easily, because all three terms have an x to the m. I have x to the m. Now if I factor that out, that's going to leave me with m times m minus 1 minus 2m minus 4 equals 0. Wow. So that really did change things, right? Because now I can multiply this m out, and I can write this as a quadratic. So I have x to the m times m squared minus m minus 2m minus 4 equals 0. So I have x to the m times m squared minus 3m minus 4 equals 0. Now x to the m will never be equal to 0. There's not a power that I could raise this to and make it 0. It could approach 0, but there's not a power that I could raise that to make that 0. So that means that, hey look, I have an auxiliary equation. And if it factors, which I hope it does, then we're going to be able to easily solve for m. So m. So if I have minus 4 and plus 1, that would give me a negative 4 when I multiply the two constants. That will give me a negative 3m in the middle. So I'm going to get m, I'm going to call it m sub 1 equals 4, and m sub 2 equals negative 1. So what does that mean? That means that I can write our solution, which if it's a homogeneous equation, we don't really have a complementary and a particular. We just have a complementary. There is no particular solution. So I'm going to have y equals c sub 1 x to the 4th minus plus c sub 2 x to the negative 1. And that's my solution. Of course, the homogeneous equations that are the differential equations set equal to 0 are a lot easier to work out. Now, I want you to look at something though. I want you to look back at the differential equation here. The way that you get the auxiliary equation is not exactly the same as the way you get it with the e to the alpha x approach. Because look at our auxiliary equation. If I was to get this using the e to the alpha x approach, like we have been doing, then that would be, I would need just I couldn't do an x right there. That x messes everything up. So I would want it to be like minus 2y prime, then I'd have minus 2m. Well, when we have x times our differential equations, we're able to work it out using x to the m in a way so that when we factor that x to the m out, we're going to get an auxiliary equation. It doesn't exactly match up with the original differential equation. If you remember, right here, the middle term ends up being b minus a. So you have a number in front of the m squared, but the number in front of the m is b minus a. Okay, so in your differential equation right here, the a here is equal to 1. The b here is equal to negative 2, and the c here is equal to negative 4. So if you wanted to skip all of this factoring, what you could do is for this middle term right here, you see where I got a negative 3 when I went through and factored out and simplified? That negative 3 is actually b minus a. Because b is negative 2 and a is 1. Negative 2 minus 1 gives you 3, or negative 3, right? So if you remember that the middle term of the auxiliary equation has a coefficient of b minus a, you don't have to do all this factoring every time. There's nothing wrong with doing the factoring every time. Just know that, you know, either you learn b minus a or you learn just factor it every time. I'm fine with you doing it either way. You know, me personally, b minus a makes more sense if you can just remember that part. All right, so that's case 1. Case 2 is repeated real roots. All right, so with repeated real roots, that would mean m sub 1 equals m sub 2. So that would mean that the discriminant part of the quadratic formula was equal to 0, right? What was under the radical ended up being 0. Or you factored it and you got the same number. Okay? So m sub 1 has to be equal to the negative of b minus a all over 2a. This is the middle coefficient, right? In the quadratic formula, we usually have the b as the coefficient of the term in front of x, right, to the first power. But here, remember how we get this negative 3? It's b minus a. So m sub 1 is going to be the negative of b minus a over 2a. So changes up the problem just a little bit if you have a repeated root. Okay, the y sub 2 can be found, y sub 2 can be found by first writing the equation in the standard form. Remember what standard form is. Standard form is where you get the second derivative by itself. Now that's going to have consequences because remember what's in front of a Cauchy-Euler second derivative, an x squared. So then you're going to divide this by x squared, and you're going to divide this by x squared. So that's going to change your differential equation into the form y double prime plus b over ax y prime plus ax squared y. No, I'm sorry. C over ax squared. C over ax squared y equals 0. All right, so to find this other solution here, we have to take a look at the p of x. The p of x is the term that's in front of y prime. This was p of x in the standard form of differential equation. This is q of x, but we're only worried about p of x. So p of x equals b over ax. And the integral of p of x would then be equal to the integral of b over ax, which if a and b are constants, that's just a natural log integral, because we're integrating 1 over x. So that would be b over a times the natural log of x. So if that's your p of x, y sub 2 would be equal to x to the m sub 1, whatever we figured out our m sub 1 was equal to, x to the m sub 1 times the integral of e to the negative p of x, so e to the negative b over a times natural log of x, over x to the m sub 1 squared dx. Alright, so if you do that, I'm getting to a formula. So you're not going to have to remember this formula. I'm showing you what the second solution would be with a repeated solution. What was the second solution the other way? Well, remember we have y equals e to the, would be c sub 1 e to the m sub 1x plus c sub 2 x e to the m sub 1x. That was how we got our two solutions previously if we had a repeated solution. Well, now how do we get our second solution? How do we handle that repeated solution? We have to work out this integral and multiply it times that. Well, I'm going to show you what it's equal to so you don't have to do it every time. That's x to the m sub 1 times the integral of, we have a property here with e to the natural log of x. If I move that up as the power, then the answer is just the power. So it would end up being x, the answer would be just x to that power, because natural log is log base e, and that's a logarithmic property. So you'd have x to the negative b over a times, if you moved this up, power to a power, that would be 2m sub 1, then that would be times x to the negative 2m sub 1 dx. Alright? So it turns out that if we add these together and we integrate, that we're actually just going to be integrating 1 over x because of the way that m sub 1 is defined. And we all know how to integrate 1 over x. That's natural log. Alright, so how do we actually write our second answer? We write our first answer as x to the m sub 1, c sub 1x to the m sub 1. We write our repeated answer as, you have to put this term in there now. So instead of putting just another x in front like we did previously, we put a natural log with the second answer that's repeated. So you write the same answer, but after that you put natural log of x. Okay? That's where we'll pick up next class meeting.